Okay.
Take it away, Dana.
Okay. So let me share my screen here, I think. Can you see that? Can people see that? Yes.
Yep.
Yeah.
Okay,
And
good.
David, do you want to say how this is going to work?
So I am just about to start. Yeah, so this is
I will
a
mute
sort
myself
of
now.
introductory exercise that Nick conceived of, and I sort of started to play along. I think I'm on board with it, but yeah. So what we're going to do is this is just going to be kind of introductory. We want to get to preview all of the topics that will be covered in the summer school, and as you know, the summer school is going to focus on variability. And so we want you to review the topics and sort of think about how each topic involves long-term variability, long-term defined elastically. And I'm going to go through, since one of the things I do is teach basic physics to freshmen and sophomores, I'm going to just sort of remind us as physicists what kinds of variability we typically encounter. And then we're going to ask that you go through, find these kinds of variations in the topics we're covering and categorize them similarly. So what I'm going to do is actually show you some analogs, right? Like simple things that you hopefully have encountered and how you discuss them. And then we want you to apply that kind of thinking just in a discussion. Is that right, Nick? We're just going to have everyone sort of discuss and in their groups come up with these categories. So let me just say, here are some of the categories that we would be looking for. Well, actually, not all of them will occur, but orbits and revolutions. I'll show you some examples of that, and various versions of oscillations. Okay, there are also things that just basically decay over time. Maybe that happens. That tends to happen once and then never again. And then there are transient events, which is not the topic of this summer school. It was the topic of last year's summer school. So again, if you find those, then maybe the organizers didn't really think through the topic very well. But hopefully, we've got things that are fall in the first three or maybe even first two categories. So basically cycles of various kinds. And let me just say for oscillations, we've got a couple of versions of this. One is just a simple oscillator. And this is something that just by itself oscillates in time. The more interesting things and things we're going to encounter more often are oscillations at multiple frequencies. And I'll have you look at this little YouTube video here. Maybe I can mute it. It's of a nice little demonstration of a pair of coupled pendula. We'll discuss this in a second. This occurs and it makes each pendulum by itself looks like it's not really oscillating periodically, but in some more complicated fashion. And finally, we'll have the good old forced oscillator. Something is forcing it at a given frequency, and what you're observing is a response to that forcing. So for instance, oops, I think we want to go here. The first thing that you learn in freshman physics about oscillations is a simple harmonic oscillator, right? A spring and a mass. And just to remind you, but also to give ourselves some terminology that we can all think of, we've got this little spring that I've drawn using PowerPoint, and we've got a blue mass, and the dashed line shows the equilibrium position of that mass. And of course, when you start off, the spring's compressed, you have all the energy as potential, none is kinetic, and then essentially you have an interchange between potential and kinetic energy. So rather than going into the details like you did as freshmen of what a simple harmonic oscillator is, just think of it as something that has its own period of oscillation, and that period is governed by how rapidly you can convert potential energy to kinetic energy, and then kinetic energy to potential energy, and it just goes back and forth and back and forth. Fair enough? That's kind of simple. And then, of course, there's an analogous thing. Another simple harmonic oscillator you probably learned about in freshman is an LC circuit, and that is a capacitor hitched up to an inductor. and that oscillates also periodically in time. And what it exchanges here is electric field energy. When the capacitor is charged up, you have electric field between the plates, and that is discharged through the inductor, which then creates magnetic field energy, and then that in turn charges the capacitor, and it gets converted back to electric field energy and so forth. And again, the period here is governed by the rate at which you can exchange one thing for another. Fair enough. Any questions? Anyone want to chime in with observations about these simple oscillators that you studied so long ago? Okay. If not, here is a version of what happens. This is the little video you watched. I'm going to have to do something so that I don't interfere with myself here. Little video you watched, and this is a version where you have two pendula, and they're coupled by some very weak spring, say. And if you watch the video, if you look at the bottom, this is my version of what that looks like, and you'll see one of the pendula sort of comes to rest, and then the other one comes to rest. And you'll hear some non-physicists talk about this in terms of transfer of oscillation from one to another. But of course, as physicists, what we do is we think in terms of normal modes. And that is the two things at the top show you ways in which this system can oscillate periodically, a pure oscillation. And in one, the symmetric mode, the two pendula oscillate together, and the spring doesn't do anything, so they basically oscillated exactly the way a simple pendulum would. In the second mode, they actually anti-symmetric, they oscillate out of phase, and the important thing is that means the spring gets stretched and compressed, and it adds its energy, its restoring force to the mix, and so mode 2 has a slightly higher frequency. So what I'm trying to sort of motivate for you here is that you have really a system with 2 degrees of freedom, so it has 2 frequencies. But both of them are pretty fast, right? I mean, they're very similar. And so when you look at the whole system, you have a superposition of these 2 frequencies. And I hope you're all familiar with the idea that when you add 2 frequencies together, 2 signals at 2 different frequencies, they can beat against one another. And that gives you a longer term variation, much longer than either of these 2 oscillators, these 2 modes oscillate at. And you get this envelope that looks sinusoidal. It is in fact sinusoidal. And the period really has to do with the difference between these frequencies. So this is one of the ways we're going to see long-term variation is when we have multiple frequencies. Now this is just 2 frequencies. And so let's see if I can go on to another one. This is going to be a movie of just, if you look in the upper right, of just a string, just an ordinary string. Now I made it in a weird shape to start with. That's why I don't have a real movie of this. I want someone just to unmute and tell me how many degrees of freedom do you think a string, this is a string, there's no mass at the end, it's just by itself. How many degrees of freedom, right? The 2 pendula had 2 degrees of freedom. There's 2 ways it could move. 2 variables will describe the whole thing. How many degrees of freedom does a piece of string have?
Single.
Oh, I didn't hear the answer.
Sorry, 2D.
Yeah, just in 2 dimensions. Yeah. How many different normal modes is it going to take to describe this shape? The shape of a piece of string in 2 dimensions.
Maybe people can put an answer in chat.
Or in chat if you don't want to just unmute. Of course, I can't see. I'm not looking at chat, so Nick will have to tell me.
I got it.
What? Okay.
Nope, no answers yet.
No answers.
So many.
Many.
It's a continuous string. Yeah, it's a
Yes, it is.
continuous string. So there's infinite number of modes.
Infinity. That's the right answer. Yes. Many is close to infinity. Either one is good. A real string, yes, not really infinity, because you can't bend it into arbitrary shapes, but a lot. and infinity is a good approximation of a lot. So now we're going to have a situation where this is going to oscillate, and on the upper left, I show you some normal modes. So let me just show you a movie of this. I'm pretty proud of this. The string on the right, in my opinion, looks pretty darn realistic looking. No string was used to do this. I just simply added the normal modes together. I think on the right, I'm adding not infinity normal modes because I don't have that kind of computer power, but I think 40 or 50 normal modes. And I show you 3 lowest frequency normal modes on the left. So if you really concentrate, you'll see that or if you really look carefully, the ones on the left are oscillating periodically, perfectly sinusoidal. In the bottom, I've graphed each of those sinusoids in sort of a light gray with the symbol following along as it oscillates. And then in this darker black, I'm plotting the end of the real piece of string. And I hope you can agree with me that what you see is not at all periodic, right? It goes through a very complicated motion. Now, this is not chaos. I know some people talked about chaos. This is a linear system. I'm just superposing normal modes, but it is aperiodic because these frequencies never sync up. They're unrelated to one another or incommensurable. So this is something else that we're going to see is systems with many degrees of freedom will basically get to a position where they add up their normal modes, and we'll see some variability that looks like it has an overall periodicity, but a complex envelope that doesn't look like any kind of periodic system. And that's just because we have so many degrees of freedom. So these are 2 cases where the oscillators are kind of doing their own thing, in this case, many things, and they simultaneously generate these periods. There's a totally different source of periodicity that we see, and that really is steady motion, right? But the steady motion is in an angle. So for instance, the rotation of an object, of a star or a planet, you can't really say that that's periodic because it's just steadily rotating. And the same for orbits, although if they're not circular, they're not, it's a little more complex, but it's still periodic. And these are sources of periodicity we'll also encounter. And you can't really say that a spinning planet is exchanging one form of energy for another form of energy and back and forth and has a period because of the conversion process. It's just rotating. So obviously the Earth rotates at a 24-hour period, 23.9 whatever, but we'll just call it 24. I misspelled cycle, but that's the source of, say, the cycle of day and night. The Earth also orbits the sun, and that has a period of 365 and some days. And this is when you combine it with the axis of the rotation. This is what gives rise to these annual seasons, right? Spring, you get them. And the moon orbits the Earth, and that's what gives rise to the phases of the moon. Again, not really an oscillation so much as a steady motion in angle. And finally, we have the situation where we can say, if we have one of these forms of oscillations or periodicity, if that impacts another system, it can drive periodic motion, and it always drives it at the driving frequency. So here's an example that we kind of all know, and you know, weather forecasting is pretty difficult, but not if you're willing to accept a pretty simple outcome. So on the bottom, I show the sunlight incident on the ground in Bozeman, Montana. This was in 2010. That's when I had the data for. And you can see it goes up a little over a kilowatt per square meter. It's brighter if you think about a plane normal to the sun, but we're up a pretty high latitude, so the sun doesn't strike normal to the ground, but in July it strikes as high as it's going to. And then, of course, you all know when the sun goes down, it's dark and there's zero incident sunlight. So you have this rather simple, although it's not purely sinusoidal, variation in the sunlight incident. And then if you look at the air temperature in Bozeman, this is sort of what air temperatures look like in July. They oscillate as well. And this oscillation is not intrinsic, right? I mean, if we didn't have the incident sunlight varying periodically, the temperature wouldn't vary periodically, but it does vary periodically. You can see it's not a simple oscillation, and that's because there's many factors at work. But I also want to point, this is something most people know, the peak incident sunlight comes right around local noon, but the peak temperature lags that. There's a phase lag. Does anyone remember from freshman physics, one of the simplest explanations, if you just drive an oscillator with a motor, there will be a phase lag between the response, that is the position of the oscillator, and the driving. Do you know, can anyone recall what is sort of the main factors in determining that phase lag? And you can unmute if you want. We'll just, if everyone's got this answer all together, that's okay. It's a simple harmonic, driven harmonic oscillator. Right.
Sorry, I was trying to find my mute button. All right, so we got a few
Okay.
things in chat. The driving frequency is not equal to the resonant frequency.
Exactly.
Damping.
Right.
Inertia of the system with a question mark, or the natural frequency of the system. Right.
And also damping. If the system is damped, that will also cause it. But yes, so somehow this is saying that the temperature, the air, at least in Bozeman, but the air everywhere, would have a natural frequency, and it has some damping. That is, if you heat it, it sort of damps out any local changes. And so that's what you get. That's what causes these phase lags. And we're going to see this in many of the systems we look at. When there's a periodic driving, you will get the response at that frequency, even if the system has its own frequency it would prefer to oscillate at. And here's just a picture here. I want to just do a little bit of interesting aspects of weather. This again is the July driving, and I Fourier transformed it with a little windowing, and I get some peaks. And not surprisingly, there's a huge peak with a 24-hour period. That's due to the rotation of the Earth. We also get a peak at 12 hours, and we get a peak at 8 hours. And the temperature has vestiges of most of those peaks. The 12-hour peak is surprisingly kind of lacking, but let's look at just the driving function. So when I Fourier transform this sinusoid, why do I get a 12-hour period, and why do I get an 8-hour period? So in other words, the second harmonic, or first harmonic, I guess is what we call it, and the second harmonic are both present in the driving. Any thoughts? Let's see, I think I can kind of. No,
couple of thoughts. One is a question about windowing.
Right. Windowing. Yeah. Sorry, I shouldn't have even thrown that out. I often use this to illustrate for upper division students. That basically means I treat the data in such a way that the fact I have only a finite amount of data doesn't cause artifacts. We can talk more about that, but it's something you have to do if you're really trying to turn observational data into Fourier. If you're going to Fourier transform observational data, it's just a term of art. But let's not.
Yeah, I understand.
Let's just say I did everything.
Hello.
Pretty right. Okay.
Right.
So I think Prasad's question was, what does windowing lead to spectrum leaks?
Nope.
Or spectral
it's supposed to avoid spectral leaks. Yeah.
Right. Okay.
These are really there. These harmonics are really part of the signal.
And then, of course, 12 hours corresponds to a day-night cycle.
Okay. But if I Fourier transform a sinusoid with a 24-hour period, day, night, it's going to only give me a 24-hour period in it, right? So, but as I said, this isn't really a sinusoid. There's a bit of a sinusoid in it, but.
So, and then finally we get atmospheric harmonics and traveling waves.
No, I'm just looking at the sunlight, the kilowatts per square meter, what's known as the insolation. So the first thing, I'll just give this one out there. The harmonics are caused because I basically don't plot negative values of the sinusoid, right? There's no idea of the night is not a negative brightness, it's zero brightness. So basically, if you take a sinusoid and chop it at the bottom like this, if you chopped it exactly symmetrically, you would get only a 12-hour period, and then I guess you'd also probably get a half of that, a 6-hour period. But that's the origin of that. But any idea why I get an 8-hour period? And I'll throw this out. If I've plotted the same data for March, and that 8-hour period is not there.
So there's a couple of other suggestions in chat about tides and possibly about moonlight,
No,
but I don't think those are in this data set.
That's good thinking. We'll get to tides in a second. That's my last example. I think then we'll be done. No, it's really that the day is not is longer than the night, but it would also work if the night were longer than the day. So I haven't chopped it right in the middle, and so I get this extra second harmonic. And as I said, in March, which is much closer to the equinox, I would basically take a sine wave and I'd cut it in. I basically rectify it at 0, and then I lose that harmonic. Anyway, so that's an example of a driven oscillator. And here I was just Fourier transforming the driving. The response, which contains all the things people suggested, is in there. I mean, it is Fourier, all that stuff is in there, but the Fourier transform really reflects mostly the driving. And the last one, people were talking about the tides, and here's another example of a driven oscillation. We have the moon going around the Earth, but actually the Earth is spinning much faster about its own axis. And what happens is the gravitational field gradient from the moon and the sun a bit, but they've only illustrated the moon here, distorts the Earth into an ellipse, or distorts, let's just put it that way. It distorts the Earth into an ellipse, and that creates these 2 tidal bulges. And we get 2 tides per day. And again, you see the lag. And that's again for the same reasons. The Earth has its own resonant frequency, and there's also some damping, and so that causes this lag. Over here, I've pulled down off the web a nice plot of the tides. I believe this is in Vancouver or British Columbia somewhere. And I think it's pretty self-explanatory. Now you see nice blue oscillations. The yellow is daylight. So this is plotted versus local time. And maybe you can sort of see, if you look around the 7th, 8th, 9th of the month, the peak tide is not at local noon, and that's the lag. You're observing the lag. But you'll also see, if you go up to earlier times, like the 1st, 2nd, 3rd, or later times like the 14th, 15th, 16th, now you are seeing something that doesn't look as sinusoidal, right? So it's a modulated sinusoid. This is being driven, and it's being driven, as I said, with more or less a 12-hour period. But we see something that's a little more complicated. Does anyone, and I'll point out the phases of the moon are nicely plotted here in the little icons. Does anyone have an idea why we don't see a simple sine curve for the tides?
There's a question in chat while we're waiting on that.
Okay.
Which is, how do you determine the natural frequency of a system like the ocean or the atmosphere?
Well, if you're an experimentalist, you'd like to just sort of give it a kick. That might not, people might not appreciate that. So more or less you have to do it for models. This really does have an infinite number of frequencies, just like a piece of string. There's an infinite number of normal modes. The ones that really will affect you are the ones that are close to a 24-hour period or 12-hour period. But you know, the ripples on the ocean can have periods much shorter than that, and I think a little bit longer as well. But sorry, that's not really an answer, but it's just basically solving the same way you would solve for a piece of string. It's more complicated. You're trying to solve for the water as well as the crust. The water is the thing that really we're interested in when we have tides. But it's a dry.
So and then Vicky is saying that the sun and the moon are not synced up,
right?
Which is why we get the, going back to your original question, I think.
Exactly right. So it's the basically they're both creating tides, and neither of them is 24 hours because the Earth, well, one of them is 24 hours. That's right. The sun is always at local noon, whereas the moon goes around the Earth, and therefore we have a frequency that is a little bit lower. I believe it's lower. Yeah, it's lower than the other one. And so it's the beating of those two frequencies, just like with a pendula, that gives us a 24-hour, a full month oscillation. And here it is plotted in some of the more remarkable tides on the planet. This is the tides at Mont Saint-Michel along the Atlantic coast of France. And here you see the tides are getting up to 11 meters, even 12, 13 meters. It's really remarkable. And you can see it's just a superposition, almost a superposition of two sine waves. We could even discuss the details there. So at full moon, you have what's known as and at new moon, you have what's known as a spring tide, where the two are in phase. Both the sun and the earth are pulling, moon are pulling in the same direction. So we get our highest tides there. And at quarter moon, you get what's known as a neap tide. This is real nautical lingo, where the sun, which is a slightly weaker contribution, is canceling part of the tide from the moon, and we get this oscillation. But I just wanted to show you this because it's an example of something that's being driven at two different frequencies, slightly different frequencies, and then we see this variation because of that frequency. Now, the moon's tides are not at a 1 month frequency, right? Neither of them are. They're both close to a 12-hour frequency. 12-hour period, but they are slightly out of phase. And so that's how we're getting this long-term variation, long-term being over the course of a month. And I think that's all I really wanted to give you by way of some physics examples of the kinds of oscillations that we're interested in. I love talking about this, but really we're interested in the weathers in space, the kinds of systems that oscillate in the between the sun and the Earth's space and the heliosphere, and how those oscillations and cycles are found throughout our system. And I will turn the rest over to Nick, so he can give you instructions for breaking out.
Right. So in the sort of original version of this, I also had sort of a long-term winding down or a long-term.
Right. Could you give me an example of that? I couldn't think of any examples that would appear in nature, because things that have wound down have probably all wound down by now, right? Unless they're re-excited, and then you're anyway. Why don't you just give me some examples of winding down things?
I mean, the GIF I had, or the video I had, was somebody spinning a coin on a table and having it like wind down. So that was the. So I think.
Okay. Yeah.
I think there are some heliophysics examples as well.
Okay, right.
Okay.
Right. Yeah. So there's ideas of things that are impulsively driven and then wind down over a longer period, and then basically have to wait until they're redriven, rather than being driven periodically.
Yeah, two things that came up in chat from Prasad, the sun's rotation rate, and then from Grant, tidal locking.
Oh yeah.
So here's what we're gonna do. I will share my screen. Well, first I'm gonna share this. So I sent this out, and a lot of people already jumped onto it. I'm using this for the first time, so you guys are all my guinea pigs. But I think it'll work. I think it'll work pretty well. I think we'll learn how to use this pretty quickly. So this is an application, a web application called Mural. And so yeah, so a number of you are in there. I can see you moving around already. So if you signed up, you do have to create I believe you have to create an account. Somebody give me a thumbs up if that statement is true, that you need to create an account. Okay, Brian's telling me thumbs up. So I'm going to share my screen. If you haven't done so yet, oh, okay, great. So you should be able to see my mural board with people wandering around in it now. So I've divided the mural board up into 4 different sort of sectors. When you go back into your synchronous groups, here's what I'd like you to do. I'd like you to take, our goal is to take our schedule. So you go to the schedule on the web for our structure, and if somebody needs that link, maybe Catherine can put it in the chat. And look at the topics that we're covering. And for groups, synchronous groups 1, 2, and 3, and you see your synchronous, your room number is what I'm thinking about. Look for the topics that you think belong in, like, cycles and orbits. Okay? For groups 4, 5, and 6, look at the topics that you think belong in oscillators, either driven or forced or damped or any form, coupled or any form of oscillators. Group 7 and 8, anything that you think involves long-term variability, and then all groups should look for anything that sort of doesn't belong in any of these categories. And the way to do this is you should be able to go to the left and grab one of these sticky notes here, and you can start typing in it. Right? And so, and then from that you can tell me what the particular topic that we're covering is. So I figure this is probably 10 minutes, and then that'll run us into our next short break, which is 10 minutes in case people have to get up and stretch or take care of something. And so we'll go into breakout rooms, work on that, and then take a quick break, and when we come back, we will we'll review what our schedule, our agenda for the next couple of weeks. Okay. So Catherine can send us to. Oh yeah, great.
Okay, we should have everybody.
Great. All right, I'm going to do something dangerous, which is share my desktop.
That is very dangerous.
Yes. So you should see me pointing at the schedule and then pointing at a presentation.
Right.
Is that right? You don't see my CNN feed.
No.
I can close. Okay, great. Okay, so first off, at least one or two groups had some questions. Like as they read the schedule, they were like, "What's that?" and that is less about your knowledge of the topic and more about us not being careful about jargon and acronyms and that sort of thing. So, for example, a couple of groups said, "What are GRCs?" And so those are galactic cosmic rays. And so specifically, back in the day.
So I'll also point out, Nick, there's also a typo there.
What
GRCs,
is?
it should be GCR.
Galactic break. Oh,
rays.
All right.
That's okay.
Well, I blame my dyslexia on that one.
Yeah.
So, Dr. Dyslexia strikes again, as my ex-wife used to say. In any case, so right, so maybe that was the confusion. But yeah, galactic cosmic rays are should be we'll fix that typo, and they should be separated from. Back in the day, it used to just all be cosmic rays. Anything that came from above the atmosphere that was high energy and hit the atmosphere and did its thing were cosmic rays. I think the sort of development of space physics began to understand that some of these were coming directly from the sun, and so those became solar energetic particles. And then some of these are coming actually from the cosmos, from outside of the solar system, and those are galactic cosmic rays, typically generated via supernova and other energetic events, and entering the solar system and impacting on our upper atmosphere and throughout the solar system. So that's one of those things. Other questions about that people had about the schedule as they got to look it over. What does something mean? What are we covering in that portion? While I find the mural, I got to find the mural. I think I've lost the mural. Did I close it? All right, well, let me try and reopen it. Yeah, sign me in. All right. So let me go through then. Let's open that up so I can reference it. I'm going to go through a little quick presentation that I put together. And Dana can kibitz and watch for chat questions. I think I'm going to skip out of that and not do it. I'm just going to do it not in presentation mode. So cycles and orbits. So for the most part, I think it's not quite trivial, but these are pretty straightforward. We're concerned primarily about the rotation and orbits of the sun and the planets. So the rotation of the sun drives a lot of things, including the dynamo. So dynamos probably showed up in there, and the solar cycle as part of this. Although for the solar cycle, the cycle isn't the key word there. It's the fact that it's driven by the rotation of the sun that puts it in this category. Based on my discussion with Dana.
Well, I'm going to quibble with that.
Okay, quibble with it.
I think of the dynamo, and I think I put in a slide from Andres Munoz Yaramillo's wonderful talk from 2015. The dynamo is kind of an oscillator by itself. It converts, instead of kinetic and potential energy, it's converting poloidal magnetic field energy to toroidal magnetic field energy, and then toroidal magnetic field energy back to poloidal magnetic field energy. So there's no driver, it's just a spontaneous oscillator. This is one of the few, actually maybe the only one in our discussion, where these things are basically just spontaneously oscillate by themselves.
But it's a requirement that the sun is rotating for this oscillator.
Sure, but that's not like a driver. I mean, that's like saying
Okay.
a simple harmonic oscillator is driven by the spring. No, it's required. You need a spring to develop a simple harmonic oscillator, but that's not the thing that drives it, right? It
Okay.
just oscillates by itself. And here, yeah, you need the sun to be rotating. You need turbulence. You need stuff like that. But those are the ingredients, and then somehow you put them together and it oscillates. And what we will discuss is why it oscillates at the period it does, why, and then things like that. But I definitely think of the simple harmonic oscillator as a spontaneous just oscillator.
Okay, and we don't disagree.
Right.
So we agree on that. So I think just because somebody calls it a cycle doesn't mean that it's just a simple rotation or cycle like a clock or something like that. It's it has a cycle in it. And of course other cycles such as the Earth's orbit, which because we're tilted gives us some a variation in the sunlight that's hitting different portions of the Earth at different times. So that's gonna show up, and tidal driving, which is not important because of the ocean tides, but it's important because of the atmospheric tides that get driven, that do some driving into the upper atmosphere, and then and the ionosphere and the thermosphere. So, but again, that's part of cycle because the moon is orbiting, right? But then all of these things also become oscillators. So we start to think about the complex oscillations that Dana and Amitava will talk about on day 3, with some discussion about why do the planet and the sun have magnetic fields and the dynamo basics. And also then next in the second week, Nick Featherstone and Saban Stanley will discuss the dynamos of the sun and stellar dynamos in the stellar interior, and then planetary dynamos. And so you shouldn't, not to, the Earth's magnetic field and the sun magnetic field are driven by the same physics, although they're in very different regimes. And so, when I learned that was kind of a revelation to me. So the other interesting thing in terms of cycles that we'll get into is galactic cosmic rays and solar energetic particles. And this is a proxy for solar energetic particles in the upper atmosphere is the concentration of what's Be? Barium. No, not barium. Beryllium. Thank you. Beryllium in I believe in ice cores. Yeah, in ice cores you can go back and see that concentration varies over an 11-year cycle, and that is an indication of the solar activity. And then GCRs, I did it right this time, are out of phase with that for reasons that will be discussed I'm assuming by Marav Ofer when she talks about the structure of the heliosphere. And we'll also have a specific discussion of GCRs On the second week, who's that speaker? On week 2 on GCRs. Oh, Joe Giacalone. Giacalone. Thank you. Let's see. So that's that. That's that. Oh, so I wanted to mention again in the ionosphere. I mean, this is a cursory example, but the solar variability throughout the solar cycle. So this plot is in the text someplace, but I got it from someplace else. The green line is the black line is the irradiance of the sun across all wavelengths. So in the IR and visible spectrum, we've got this nice black body curve, but then we've got lots of spectral lines, very discrete spectra in the UV and X-ray regions. And so for the most part, the variability in the IR and visible spectrum is pretty low. So it's down to fractions of a percent on this green scale here, but then it jumps up to quite high, either somewhere between 1% and 100% of variability. So you can get twice as many twice the X-ray flux and 10% more EUV flux, and etc. During solar maximum than you get during solar minimum, and that of course drives the ionosphere differently at solar minimum and at solar maximum. So, and that discussion will happen late next week with Shasha Zhao. And then what's the last thing I have? Oh, long-term trends. So somebody pointed out that there's, the fact that the sun is winding down, and also so Dana, you put this in here, is that right? Did you move this to the magnetic striping in the, or did I do that?
I think you put that in.
Oh, okay.
I'm going to talk about it in my lecture on Wednesday.
Yeah. So it's part of, so there's a question as to whether it's part of some complex oscillation or but it goes on long enough that maybe like part of a long-term trend or winding down. Certainly if you look at this
one of the points I'm going to make in my lecture on Wednesday is really this is a case where the dynamo itself seems to have lots and lots of frequencies. It's more like a multi-frequency, like that piece of string, which is trying to oscillate at many, many frequencies at once. It has many, many normal modes. And therefore, what you see is, I don't want to say chaotic, although the dynamo itself is probably chaotic. It's nonlinear. But you could even envision a linear system producing this kind of complicated behavior simply because you have so many different modes working simultaneously. And we're going to contrast that with the sun, which appears not to have so many normal modes going on. The sun is actually a little less I don't know how to say it in these terms of the oscillator, but it seems to be more periodic. It's obviously not perfectly periodic, but yeah.
Let's see.
Yes, I want to say this is an example of a long-term trend that comes from the interaction of lots of frequencies. Right, the thing is string, yeah.
Right.
As opposed to a long-term winding down, because let's face it, if the Earth were going to wind down, it wound down a long time ago. This is only millions of years, which sounds like a long time, but it's not. It's, as far as the Earth goes, this is like today. and you know, it started on New Year's Eve. So if anything was going to happen, it happened in the first couple days of January, and now we're just seeing it evolve. Now, when you see the stellar evolution, that is long-term trend, right? That's where stars are born and then they die. And things can vary over the course of their lives. So that, I guess I should have thought of an example like you did, Nick, of something that basically is just going to evolve over time and then stop.
Okay, that's fine. That's why we did it together. Where did people put David Brain's atmospheres and habitability? I'm trying to look at the giant puzzle here. Anybody put it anywhere?
It's in long-term variability.
Oh, okay. Who put it there and why? I don't know why I don't see it. I can't. Anybody? I mean, there's no wrong answer in this case. So, what's your reasoning for that?
We did in group 8. Maybe it was the wrong time scale. I feel like there's a lot of different time scales that we're working with.
There are a lot of different time scales we're working with. That's fine. So, but give me a reason.
So we were thinking that how the atmosphere, for instance, at Earth, how the atmosphere changes over time would affect the habitability of it. And we thought that was more of a long-term thing rather than a cycle.
Okay. Yep. I mean, certainly the atmosphere has changed dramatically since the formation of the Earth, and even since life evolved on the Earth. So, chat. So harmonics. So I'm sorry, I wasn't paying attention to chat. Earth's dynamo variation is so many different frequencies. Okay, yeah. So would orbital harmonics count as spontaneous spontaneous? I'm not sure what you mean by spontaneous oscillator, but such as Jupiter's moons.
Oh, are we thinking of harmonics? Basically, the harmonic relationships between the periods of the moons. Is that what you're thinking?
I think so. But Vicky, chime in if you
Yeah, I was curious about this when we were discussing how the sun's the sun's dynamo was a spontaneous oscillator and just set itself up without any driving. Now, a couple of people in the chat were wondering what other spontaneous oscillators might be, and I was wondering, yeah, is the way that Jupiter's moons kind of shuffle themselves into having related periods, would that be a harmonic oscillator, or is that something different?
I mean, these are categories we kind of Nick and I kind of invented ourselves, so there's no right or wrong answer. I guess.
So it's certainly a coupled system of some sort that has some periodicity to it. So
correct, yeah.
So sure.
Yeah, I mean, there's an example I gave to Nick, but I don't know how many people here know about the Milenkovic cycle. Has anyone heard of that?
Why don't you tell us what the Milenkovic cycle is?
Okay, so that is basically a bunch of different oscillations that are all more related to orbits and rotation. They're not spontaneous like a simple harmonic oscillator. They're just the planets are orbiting around the sun, but they do interact with one another. And so there are linear normal modes that you can actually look at. And the Milenkovic cycle is a combination of the way that the planets affect the Earth's eccentricity of its orbit. And that will vary on, there are so many different frequencies that it does look again like a chaotic curve, but there's sort of a fundamental period of, I think, about 100,000 years. And then there's the obliquity of the tilt of the Earth's axis, which is disturbed again by various interacting bodies, and that tends to become more and less tilted over periods of 41,000 years. And then the interaction between those two periods is thought by some to be what causes occasional ice ages. So in that sense, the ice ages are driven by this oscillation in periods of orbits. The same way the tides are driven by, well, the rotation of the Earth interacting with the moon. Yeah, so it's an interesting, and these cycles are very long term, as I just pointed out. The periodicity of 100,000 years doesn't come from the orbit of Jupiter or the Earth. It just has to do with the fact that those two oscillators are very weakly, not oscillators, orbits are very weakly coupled by the gravitational pull between the two planets. So that's a very weak coupling, in the same way that the spring in my little example is a very weak coupling and causes a variation in the oscillations that is on much longer periods. And here it's even weaker than any spring you can imagine, and therefore instead of being 1 year or 11 year or whatever period, it's hundreds of thousands of years, even up to, I think when you involve Neptune, it's like a 2 million year period. That doesn't really answer any questions, but it just gives you more examples where basically orbits can be involved with oscillations.
Okay, great. I was just, as Dana was talking, I was looking at the uncategorized or miscellaneous thing. A couple of comments. So there's a couple of lectures that are Dana's that we titled the Heliophysics Core, and that's a note to us that these are sort of These are lectures that actually don't change from year to year. They are sort of grounding lectures that put everybody on won't say put everybody on the same footing, but give everybody a background that we're expecting to draw from in the coming weeks. So, or the 2 weeks that those are Wednesday and Thursday in the first sessions, where Dana will be talking about first fundamentals about what's happening in the sun and the planets to give them magnetic fields, and then also what's happening in the why is there a magnetosphere and an ionosphere? So I agree. Comparative magnetospheres probably is not. Does not sort of looks at snapshots of things. So that's going to be a lab at the beginning of week 2, where we'll use simulations to look at what happens to a magnetosphere under different conditions, and as at least as analogs for what might happen at Jupiter and what might happen at Neptune when you turn the thing on its side, and et cetera, et cetera. So some of the others, so certainly the interstellar probe discussion is that's long-term variability. If you think that NASA has some long-term variability in their planning, so but yeah, that's kind of a I would agree that that's a miscellaneous category. So. And then as well as NASA's long-term plans, which I think was in there too. But I look forward to, I think those will be very interesting discussions as we start to think about how the field is going to move forward in the next 10 years. Okay, great. Any other questions or comments on this activity, or what you or the discussion of the schedule for our program for the next couple of weeks? Okay. So, Catherine, where are we on timing? I think we got.
We're 30 minutes after the hour. So we were going
to. Right, so we've got about a half an hour left. Is that right?
20 minutes.
20 minutes left. Thank you. Okay, great. Great. Then that's just enough time to wrap up what I want to. Well, so I think I'm going to wrap this up, but I want to give you a little bit of instruction for what you should be doing next. So, more or less every day of the summer school, we will meet in these 4-hour sessions, and then after that, sometime in the next 24 minutes, so sometime in the next 20 hours, you will have an assignment to work on in your time zone groups. Okay, a task. I should call it an assignment. It's more of a task. Tomorrow is going to be primarily interaction. It's our first lab. It is one of the things that does sort of not fit into one of our categories because it explicitly looks at an event. So we talked about the fact in the beginning. Dana said we weren't going to look at transient events, and that's true except for tomorrow's lab. The goal of tomorrow's lab is for you all to start to wrap your brain around the system, right? The Sun-Earth connection, the heliophysics, the heliosphere as a system. And to start to share your expertise with your colleagues as well. And to do that, what you're going to do is you're going to be given data from a space weather event from 2017. And you're going to have to make sense out of it, right? You're going to have to come up with in fact, I'm going to give you each a mural board that's blank, and you're going to have to come up with all the connections between the data and there's also simulation results involved in that show the connections in the system and how different parts of the system affect each other. In preparation for that, in your time zone groups, I've divided you up into specializations, and I'm going to stop sharing here because I have to go find that document that I put someplace. Nope, that's not it. Okay, so this will take me a minute, but before I go away and find that, let me ask this question: Do any of the time put your hand up, like put this hand up. Can I do that? Yeah, put that hand up. If you need to meet with feel like you need to meet with your time zone group and find out where schedule a meeting in the next 24 hours, 20 hours. Okay, so Prasad's group. All right, great. So we've got a few different reactions here, but Catherine, are time zone groups set up easily, or?
I can go through and set them up here right now, so that would be helpful.
Maybe. Why don't you do?
We're not going to use sync groups again, right?
We are not going to use sync groups again. No, we're done with that.
Okay, then yeah, it'll just take me a few minutes, but I can certainly do that.
Okay. I'm gonna find a document that I put together. And I'm sorry, I thought I had this open someplace, but I've lost it in the myriad of windows that I had. Yeah, here it is. Okay, great. I'm just going to share this with you all. And I will also put this, you can take a look at it now, but I will also put this on the Slack channel for people to reference. So, and the other thing I will share, I hope. Yeah, good. Is I'm going to share this with you all. Okay. Whoops. All right. So the first thing is broken. That's not what I wanted to do. So I am ignore that. The second thing should be it should say, when you open up, it should say tracking a solar storm. Okay, I'll fix that in a minute. How about that one? Does that one open? That should say, that should be Lab 1 TZ groups.
Still says we need access from you.
Yeah, all right, fine. Oh, shoot, that's the wrong, hang on. Okay, so I see a bunch of people in tracking solar storm. Is that right? Somebody give me a thumbs up. Great, thank you. And then I don't see anybody in the time zone group, so I'm going to change that to commentator. All right. So you may have edit privileges, but please don't edit this. All right, somebody check that second link. All right, here's what I'm going to do. Hang on. We'll do this the hard way. Files. My computer. Downloads. What do they call it? All right. Okay, so here's how I have this organized. Do you know what your time zone group numbers are? Yeah, okay, great. So under under there are 4 different four different domains that we've broken this up into: solar, solar wind, magnetosphere, and ionosphere. Okay, so each group should be listed in a domain if I did this right. And then I'm giving you each I created a separate document for each of you to use. It's a blank document, and you should be able to. Okay, so those need to be so access needs to be allowed for that. I'll make sure I can fix that. The idea is that ultimately you're going to have to share this amongst each other. So if we can use that document, that's great. Your assignment for spend approximately 1 hour in the Tracking a Solar Storm manual. Right, there's a little bit of introduction, and in your expert groups. So the solar is this first expert group, solar and coronaspheres. The solar wind groups are there. The magnetosphere is another group, and then the ionosphere is yet another group. There's specific data and simulation results for you to look at. You should, as part of that, start to summarize your answers to these questions and individual questions under your specific group. So everybody for all expert groups should answer these questions in bold here, and then each expert group has its own set of questions to look at that are specific to that data set. All right? So spend some time becoming familiar with that. When we start, the first thing you'll do is you'll start to share your results with the other groups that looked at the same data. Okay, so there's at least two solar groups. There's at least 2 of each group, and I think there's 3 of one group, right? So, and then what you're going to do is you're going to break up into other groups, and I'll give you some instructions on how to do that, primarily through your synchronous groups, to try and put the whole event together and understand what the whole event looks like and how it all connects up. All right. So, but your assignment tonight is just to start to look at this data and start collecting the answers to those questions. All right. And I hope I've tried to make this easy to organize so that we can share materials. I'll go back into these various documents and change the permissions so that you should be able to see them and edit them. And anybody with a link should be able to see them and edit them. All right? Questions on that? Great. Okay.
Actually, I do have one question.
Yeah, please.
So the overall structure is just that after we finish up for the day as a big group, it's sort of our responsibility as time zone groups to find times that work for us and work together on those assignments in preparation for the next day. And that's just the overall structure. Okay.
Yeah.
Thank you.
Yeah, so expect that to happen pretty regularly. Okay. I think we're done. If, as a time zone group, you feel like you know when you're going to meet or have a plan to meet, great. If not, hang on. So, so first off, Dana, I think we're done, right? Great. Okay.
No, yeah.
So if you need to figure out, as a time zone group, if you need to figure out a time to meet, hang on. We will we'll wait and we'll put you in a breakout room. You can talk about it. Also, twice a day during this synchronous time that we're all together in the break, right? The longer break in the middle, and then after we're done with the day, we will have office hours, and we will usually have the speakers from that day in the office hours immediately following their talk. So if you've got a reason to ask questions of them, or you just want to chat with them about something, talk to them about some interesting physics that you're doing, you should feel free to share that. They are just as interested in hearing from you as you are from them. So that's a time to do that. It's a replacement for after the talk is done and we're going to coffee or going to lunch, and you can collar the speaker, right, as they're trying to wrap up their computer and ask them specific questions, right? So this is a time for you to do that as well in this venue. So just to let you know what we will be. So I and Dana will hang around and have some office hours this afternoon for the next half an hour or so. And if you need to schedule some time with your time zone groups, then you can do that now too. So otherwise, we're done. Do your the work that you need to do to prepare for tomorrow, and we will see you at the prescribed time tomorrow.
Nick, I've got the breakout groups open, so I think if anybody wants to jump into their breakouts right now, their time zone groups, they can do that.
Okay, great. So I'll have Catherine open up the breakout rooms, but we're done, so you can just leave. And it was great to meet you all. It's wonderful to start to work with you, and I'm looking forward to Dana and I and Amitava are looking forward to some productive couple of weeks of discussion and learning, and not only learning from our speakers, but learning from you. Right? So have a good night.